Hello, good afternoon. In this video we're going to take a look at four relatively easy differential equations. We're going to start off quite easy and then we're going to work towards the fourth one. So let's take a look here. Let me just activate the pen. Okay, so they ask us to find the general solution to the following differential equation. Now a differential equation normally has a dy dx in there. So the first thing I want to do is I want to make dy dx the subject. So let's go and say dy dx is equal to 1 over cotangent square of x. Now I notice that 1 over cotangent is normally tan, so 1 over cotangent squared is the same as tan squared, so dy dx is equal to tan squared of x. Now what I want to do is I want to find the general solution. In other words, I want to find the original equation in terms of y. So what I want to do is I want to go and I want to integrate on both sides in terms of dx. So if I integrate the left hand side, I'm going to get y. Y is equal to the integral of tan squared of x dx. But I cannot integrate tan squared of x. But if I look at my trigonometric identities, I know that tan squared of x is actually the same as secant squared of x minus 1. So I can replace tan squared of x with secant squared of x minus 1, and I'm going to still integrate this in terms of dx. Now the integral, my integral law says, since there are two terms, I can separate them. So y is equal to the integral of secant squared of x dx minus the integral of 1 dx. We know that the integral of secant squared is actually tan of x, and we know that the integral of 1 is negative x, since I'm integrating in terms of dx, plus c, because this is an indefinite integral, so we should not forget the plus c. So this is the general solution to the differential equation. Now let's take a look at the second one. For the second one, they ask us to find the particular solution to the following differential equation. So we will now see for the particular solution, they give us a value for y is equal to 1 when x is equal to 1. Okay, so again, let's go and make dy dx the subject. So dy dx is equal to x squared plus 1 over 2x. Okay, and of course we have when y is equal to 1 and x is equal to 1. Now what I can do here is I can separate this fraction. So dy dx is equal to x squared over 2x plus 1 over 2x, and x squared over 2x can be simplified further as a half x plus 1 over 2x, and I still have dy dx. Now let's go and say we want to integrate this to find the original equation. So if I take the integral on both sides, y is equal to the integral of a half x plus 1 over 2x, and then I am integrating in terms of dx. Now let's go and quickly integrate this. So a half x, the integral of x means x is to the power of 1, so I'm going to add my power, so x squared multiplied with a half in front, so this will become 1 over 4 x squared, and the integral of 1 over x is normally natural log of x, so I can keep the half outside, natural log of x, and then remember I have a plus c here. But now since it is a particular solution, we can actually find the value of c, because they said y is equal to 1 when x is equal to 1. So I can go and substitute this in here. Y is equal to 1 when x is equal to 1. So 1 squared stays 1, so it stays 1 over 4. Now natural log of 1 is actually 0. So a half times 0 is 0, so that fades away, so then I have just plus c, so therefore 1 minus a quarter is 3 over 4, so the value of c is 3 over 4. Now let's go and rewrite this. Y is equal to 1 over 4 x squared plus a half natural log of x, and now instead of c, I have found the constant value of c, 3 over 4. And this is the particular solution to my differential equation. Now, let's go and take a look here at the third one that we have. Now, in this one here, we notice that something is different. We have dy dx is equal to sine x over cosine y. And now for the first time we notice that we have something in terms of x and y. And we say we are going to separate these two variables. So how do I do that? So I have dy dx is equal to sine of x over cosine of y. Now I know here that I am dividing by cosine of y. So if I multiply with cosine on y on both sides, I get cosine y dy dx is equal to sine of x. I notice that this is division by dx, so now I say cosine y dy is equal to sine of x dx if I multiply with the dx on both sides. And now I have cosine y dy is equal to sine x dx. What I can do is I can integrate both sides. But now I notice on the left hand side I am integrating in terms of dy, and the right hand side I am integrating in terms of dx. So the derivative of cosine of y is going to be positive sine of y, and the integral of cosine of y is sine of y, and the integral of sine of x is going to be negative cosine of x plus c. But again, let's go back to our original question. They gave us the following: y is equal to 0 when x is equal to pi over 3. And I can go and substitute this in here. So I have sine of 0 is equal to negative cosine of pi over 3 plus c. And we know that cosine of pi over 3 is the same as a half. So we have 0, because sine 0 is equal to negative a half plus c. So c is equal to positive a half. And now I can go and rewrite my equation. Sine y is equal to negative cosine of x plus a half. Now, of course, the question is not here at the top, but they could mention that we should write this explicitly in terms of y. In other words, we have to make y the subject. But luckily for us, they did not mention that we have to write this in an explicit form, so I can leave my answer like this, in the implicit form, with a sign y here as the subject. Now, let's go and take a look here at the last one that we have. Now, this one here, I am going to write it in terms of y. So my final answer, I'm going to write it explicitly. Again, I notice that I have dy dx is equal to 4y over x. Again, I have a y and an x here, and then I see I can find the particular solution because y is equal to 2 and x is equal to 1. So first, let's go and separate the variables. So if I want to separate the variables and I want all my y's on the left hand side and all my x's on the right hand side, I'm going to divide by a 4y. So I have 1 over 4y dy is equal to 1 over x, and I multiply with a dx on both sides, dx. So now that I have this, I can take the integral on both sides. Since it is an integral of 1 over 4y, I can take this 1 over 4, I can take this quarter outside. It is a constant. So 1 over 4 and the integral 1 over y dy is equal to the integral of 1 over x dx. Now, if I want to find the integral of 1 over y in terms of dy, I will get natural log of y, and I'm going to get natural log of x plus c. Okay, so of course I notice that this is a power, so what I could do is I could say the natural log of y to the power of a quarter is equal to natural log of x plus c. But again, from the original we notice that y is equal to 2 when x is equal to 1. So I'm going to replace y with a 2 and I'm going to replace x with a 1. So this now becomes natural log of 2 to the power of 1 over 4 is equal to the natural log of 1, which we know is 0, plus c. So therefore in this case, c is equal to the natural log of 2 to the power of a quarter. So let's go and rewrite our equation. So we have the natural log of y to the quarter is equal to the natural log of x plus the natural log of 2 to a quarter. Now, from my logarithmic laws, if there's a plus, log plus, I can actually multiply. So this is going to be the same as the natural log of x multiplied with 2 to the quarter, and I have the natural log of y to the power of a quarter. So, of course, I can take the log on both sides. I am left with y and 1 over to the power of 1 over 4 x times 2 to the power of a quarter. I'm going to take get the quartic on both sides, so y is equal to x to the 4th, and as it is 2 to the power of a quarter times 4, it is just 2. Or alternatively, I could have written this as 2x to the power of 4. And this is now in explicit form because I have y alone on the left hand side. And this is the particular solution to this differential equation, which is a separable differential equation. I'm separating the variables on both sides.